Some black holes will shred you into atoms before you even see them coming. Others will freeze you in time forever. And the most terrifying ones, they shouldn't even exist. Today, I'm going to show you every nightmare scenario hiding in the darkness of space. Buckle up, because this is going to get disturbing. Picture this. You're floating in space, approaching a black hole. At first, nothing seems wrong. The stars look normal, your breathing is steady, but then you notice something strange. Your feet feel heavier than your head, much heavier. Within seconds, the difference becomes unbearable. Your feet are being pulled thousands of times harder than your skull. Your body starts to stretch. Your bones crack. Your organs tear apart. Scientists have a name for this process: spaghettification. And it's one of the more merciful ways a black hole can kill you. But here's what really keeps astronomers up at night. Black holes don't just destroy matter, they destroy information, violate the laws of physics we thought were sacred, and create paradoxes so profound that Einstein himself refused to believe they could be real. He spent years trying to prove they were impossible. He was wrong. The universe is filled with these cosmic nightmares. Some are invisible hunters stalking through galaxies. Others are so massive they could swallow our entire solar system and still have room for dessert. And we're only just beginning to understand how many different types exist. Over the next hour, we're going to explore every single category of black hole that could end existence as we know it. From the ones born in apocalyptic stellar explosions to the theoretical monsters that could be lurking in dimensions we can't even perceive. This isn't just astronomy. This is a catalog of cosmic horror. So let's dive into the abyss and see what stares back. The most common nightmare in the universe starts with something beautiful, a star. But not just any star. We're talking about giants, monsters dozens of times heavier than our sun, burning so hot and bright they make our home star look like a candle in a stadium. These stellar titans live fast and die violently. While our sun will burn for about 10 billion years, a massive star might only last a few million. That's because the bigger you are, the faster you burn through your fuel. It's like throwing gasoline on a bonfire. Sure, it's spectacular, but it won't last long. When one of these giants finally exhausts its nuclear fuel, something catastrophic happens. For its entire life, the star has been fighting a war between two forces. Nuclear fusion in its core pushes outward, trying to blow the star apart. Gravity pulls inward, trying to crush it. For millions of years, it's a stalemate. But when the fusion stops, there's no outward push anymore. Gravity wins instantly. The core collapses in less than a second. The outer layers, suddenly unsupported, come crashing down at a quarter of the speed of light. When all that matter hits the core, it bounces back in an explosion called a supernova. For a brief moment, that dying star shines brighter than an entire galaxy. You could see it from across the universe. But here's what the real horror is. The core doesn't stop collapsing. There's nothing left to hold it up. Gravity crushes it past the point where atoms can exist, past the point where even neutrons can resist. It crushes matter into a singularity, a point of infinite density, wrapped in an event horizon, a boundary where escape velocity exceeds the speed of light. What's left is a stellar black hole, typically between 3 and 100 times the mass of our sun, compressed into a sphere maybe 30 kilometers across. Imagine crushing Mount Everest into a grain of sand. That's the density we're talking about. Now, you might be thinking, okay, it's dense. So what?
Here's what. If you replaced the sun with a stellar black hole of the same mass, the gravitational effect on Earth wouldn't change. We'd keep orbiting normally. We'd freeze to death without sunlight, sure, but we wouldn't get sucked in. Black holes aren't vacuum cleaners. They don't reach out and grab things from far away. But get close. That's where the nightmare begins. Let's say you're in a spaceship, approaching a stellar black hole. You decide to get within a few thousand kilometers, just to take a look. At first, space looks weird. The black hole bends light around it, so you see distorted images of stars behind it, wrapped around its edge like a funhouse mirror. As you get closer, something stranger happens. You look at your watch, 1 second per second, just like normal. But if someone is watching you from a safe distance, they see your watch ticking slower and slower and slower. This is time dilation. The closer you get to the event horizon, the more time itself slows down from an outside perspective. If you were to cross the event horizon and your friend was watching from a spaceship far away, they would never actually see you cross. From their perspective, you'd appear to slow down, getting dimmer and redder until you froze at the edge forever. But from your perspective, you'd cross in finite time. You'd pass the point of no return, and you wouldn't even notice the moment it happened. That's when the real horror starts. Because once you're inside, every direction you can move, forward, backward, up, down, leads toward the singularity. It's not a place anymore. It's your future. You can no more avoid hitting the singularity than you can avoid next Tuesday. And then comes the spaghettification. The tidal forces, the difference in gravity between your head and feet, grow stronger with every passing second. First, it's uncomfortable, then painful. Then your body begins to stretch. Your molecules pull apart, your atoms disintegrate. By the time you reach the singularity, you're not even matter anymore. You're just information being added to the black hole's mass and spin. The most famous stellar black hole is probably Cygnus X1. Discovered in 1964, it sits about 6,000 light-years from Earth in the constellation Cygnus. We can't see the black hole itself, but we can see its companion star, a blue supergiant being slowly devoured. Gas from the supergiant spirals into the black hole, forming an accretion disk. As the gas falls inward, friction heats it up to millions of degrees. It glows in X-rays so bright we can detect them across thousands of light years. That's how we spotted it. That's how we spot most stellar black holes, by the way they feed. Cygnus X1 was so controversial when it was discovered that Stephen Hawking made a bet about it. He wagered that it wasn't actually a black hole, because if it turned out not to be one, at least he'd win something to compensate for his life's work being wrong. He lost the bet in 1990 when the evidence became overwhelming. Cygnus X1 is definitely a black hole, about 21 times the mass of the Sun. Astronomers now estimate there could be 10 million to a billion stellar black holes in our galaxy alone. Most of them are invisible, drifting through space silently. No companion stars to feed on, no accretion disks to give them away, just invisible gravity wells waiting in the darkness. Could one of these rogues be heading toward our solar system? Technically, yes. Realistically, space is so vast that the odds are almost zero. The average distance between stars is about 4 light years. The average distance between black holes is much, much larger. You'd have better odds of winning the lottery while being struck by lightning. But here's an unsettling thought. There could be a stellar black hole just a few light years from Earth right now, and we'd have no way of knowing unless it happened to pass in front of a bright star. It would be the ultimate cosmic predator, invisible, silent, and deadly, waiting in the dark. Now let's talk about something even more disturbing. Black holes so small you could hold them in your hand. If they didn't instantly kill you, that is. In theory, black holes can exist at any mass. The Schwarzschild radius, the size of the event horizon, is directly proportional to mass. A black hole with the mass of Earth would have an event horizon about 9 millimeters across, the size of a grape. A black hole with the mass of Mount Everest would be smaller than an atom. These are called micro-black holes or mini-black holes, and they're terrifying for completely different reasons than their stellar cousins. First, let's talk about how they might form. They probably can't form naturally in the modern universe. When a star collapses, you can't get fragments. It's all or nothing. Either the core collapses into a black hole, or it doesn't. So if micro-black holes exist, they likely formed in the early universe, when densities were high enough for random quantum fluctuations to create them.
But here's where it gets interesting. In 2008, when the Large Hadron Collider was about to turn on, some people panicked. They worried that smashing protons together at nearly the speed of light might create micro-black holes that would sink to the center of the Earth and devour the planet from the inside out. Scientists assured everyone this was impossible, and they were right, but not for the reason you might think. The LHC might actually be able to create micro-black holes if certain theories about extra dimensions are correct. But even if it did, those black holes would be so small and so short-lived, they'd evaporate before they could consume a single atom. This is because of Hawking radiation. Stephen Hawking discovered that black holes aren't completely black. They emit a tiny amount of thermal radiation due to quantum effects near the event horizon. For a massive black hole, this radiation is negligible. A stellar black hole would take longer than the current age of the universe to evaporate. But for a tiny black hole, the smaller it is, the faster it evaporates. A black hole with the mass of a car would evaporate in a nanosecond, releasing its entire mass energy as radiation. That's about as much energy as a large nuclear bomb, in a billionth of a second. So if the LHC did create micro-black holes, they'd pop like quantum firecrackers, releasing harmless particles, and that would actually be amazing because it would confirm some revolutionary physics theories. But here's a darker scenario. What if micro-black holes from the early universe are still floating around? Not the unstable ones that evaporate instantly, but slightly larger ones that could survive to the present day. A black hole with the mass of the moon would have an event horizon smaller than 1/10 of a millimeter, but would take trillions of years to evaporate. Now imagine one of these passing through Earth. It wouldn't swallow the planet, it would be moving too fast and its gravity well too small. But as it passed through, it would bore a tunnel of destruction, flash heating everything in its path to plasma temperatures. If it went through a city, everyone in a narrow line would simply cease to exist. No warning, no sound, just an invisible bullet of gravity moving at cosmic speeds. Fortunately, we have no evidence these things exist, but we're looking. If a micro-black hole passed through a planet or star, it might produce detectable signals, bursts of radiation, seismic activity, unexplained energy releases. So far, nothing. But the universe is big and full of surprises. Perhaps even stranger is the idea that micro-black holes could be dark matter. Dark matter is the invisible substance that makes up most of the mass in the universe. We know it exists because we see its gravitational effects, but we have no idea what it is. Most scientists think it's some exotic particle we haven't discovered yet. But what if dark matter is actually countless primordial micro-black holes scattered throughout the cosmos? They'd be invisible, just like dark matter is. They'd have mass, just like dark matter is. And they'd clump around galaxies, just like dark matter does. Some scientists take this idea seriously, though the evidence is mixed. If this theory is correct, then you're being passed through by micro-black holes constantly. thousands per second, moving at incredible speeds, too small and too fast to interact with normal matter in any meaningful way. They'd fly through your body, through the Earth, through the sun, like bullets through fog. Sleep well tonight. Here's something that should concern you. Not all black holes stay in one place. Some of them are moving through the galaxy at hundreds of kilometers per second. We call them rogue black holes, and they're exactly as dangerous as they sound. Most black holes form when massive stars die. When that happens, the supernova explosion isn't always symmetrical. It can be lopsided, releasing more energy in one direction than another. This gives the newly formed black hole a kick, like recoil from a gun. Some of these kicks are gentle, just a few kilometers per second, but others can launch a black hole at speeds exceeding 500 kilometers per second. That's fast enough to escape most galaxies. These black holes become intergalactic wanderers, drifting through the void between galaxies with nothing to slow them down. No friction in space, no air resistance. They just keep going forever, unless something stops them. And what could stop a rogue black hole? Another galaxy, like ours. Our Milky Way is constantly pulling in smaller galaxies and absorbing them. When that happens, any black holes in those dwarf galaxies get dragged along for the ride. Some settle into stable orbits, others keep their momentum and pass right through, like a bullet through tissue. Now, before you panic, remember that space is mostly empty. The odds of a rogue black hole hitting Earth are so low they're barely worth calculating. But hitting something in our solar system, that's more plausible. And even a near miss could be catastrophic. If a stellar mass black hole passed within a light year of our sun, it could gravitationally disturb the Oort cloud, the distant shell of comets surrounding our solar system. This could send thousands of comets falling toward the inner solar system. Some would hit Earth. Extinction-level impacts multiple times over centuries, and we'd have no way to stop them all. The black hole itself would just keep moving, completely unaware of the chaos it caused. The scary part? We have no idea how many rogue black holes are in our galaxy. They're invisible unless they're actively feeding, and most of them aren't. They're dark, silent, and effectively undetectable with current technology. They could be anywhere. In fact, in 2022, astronomers found what might be the first confirmed rogue black hole. They noticed a star brightening in a weird way, and the best explanation was that a black hole passed in front of it, bending the light through gravitational lensing. The black hole wasn't orbiting anything, it was just traveling through space, minding its own business, 7,000 light-years from Earth. If one exists, there are probably millions more, ghosts in the darkness moving at relativistic speeds, and we're flying blind.
If stellar black holes are bullets, supermassive black holes are nuclear bombs. We're talking about objects millions to billions of times more massive than the Sun. And here's the kicker. Almost every large galaxy has one sitting at its center, including ours. Meet Sagittarius A star, the supermassive black hole at the heart of the Milky Way. It weighs about 4 million solar masses and sits 26,000 light-years from Earth. We can't see it directly, but we can see stars whipping around it at insane speeds. Some complete full orbits in just 16 years, reaching velocities of 5,000 kilometers per second, more than 1% the speed of light. Think about that. These are stars, giant balls of burning gas, and they're being flung around like pebbles in a slingshot. The only thing that could do that is a supermassive black hole. But Sagittarius A star is actually pretty quiet. It's not feeding much, it's just sitting there, holding the galaxy together through its gravity. Other supermassive black holes are far more violent. Take M87 star, the black hole at the center of the galaxy Messier 87. This monster weighs 6.5 billion solar masses. To put that in perspective, if you replaced our sun with M87 star, its event horizon would extend past the orbit of Pluto. The entire solar system would fit inside it with room to spare. In 2019, the Event Horizon Telescope captured the first ever image of M87 star. You've probably seen it, the orange ring glowing around a dark shadow. That shadow is the black hole's event horizon, and the ring is superheated matter swirling around it at nearly the speed of light before falling in. That image changed everything. For decades, black holes were theoretical. We believed they existed because the math said so and the observations fit, but we'd never seen one. M87 star was proof, direct, visual, undeniable proof that these monsters are real. But how do supermassive black holes form? This is one of the biggest unsolved mysteries in astrophysics. Stellar black holes form from collapsing stars, but there's no star big enough to collapse into a million solar mass black hole. So where do they come from? One theory is that they start small and grow over billions of years. A stellar black hole forms, then feeds on surrounding gas and stars, slowly gaining mass. Sometimes it merges with other black holes. Over cosmic timescales, it could grow enormous. But there's a problem. We've found supermassive black holes in galaxies less than 1 billion years old. That's not enough time for a stellar black hole to grow that big, even if it was feeding constantly. It's like finding a full-grown oak tree in a forest that's only 5 years old. Something doesn't add up. Another theory is direct collapse. In the early universe, massive clouds of gas might have collapsed straight into supermassive black holes, skipping the stellar phase entirely. This would explain how they got so big so fast. But we've never observed this happening, and we're not sure it's even possible under normal circumstances. Some scientists think primordial black holes from the Big Bang might have acted as seeds, giving supermassive black holes a head start. Others propose that dense star clusters in the early universe merged together, forming black holes much larger than any single star could produce. The truth is, we don't know, and that's unsettling. These objects dominate galaxies, yet we don't understand where they come from. What we do know is that supermassive black holes aren't just passive occupants. They actively shape their galaxies. When they feed, they release enormous amounts of energy. Matter falling into a black hole doesn't just disappear quietly. It heats up to millions of degrees, emitting intense radiation. This radiation can drive powerful winds that blow gas out of the galaxy, shutting down star formation. In this way, supermassive black holes regulate the growth of their host galaxies. If a galaxy tries to form too many stars too quickly, the central black hole feeds more aggressively, releases more energy, and pushes gas away. It's a cosmic thermostat. But sometimes the black hole feeds so aggressively, it becomes a quasar. And that's when things get truly terrifying. Quasars are the brightest objects in the universe. A single quasar can outshine an entire galaxy of hundreds of billions of stars. We can see them from across the observable universe, beacons so brilliant they're visible from billions of light years away.
What causes this? A supermassive black hole in a feeding frenzy. Gas falls into the black hole so quickly that it forms a superhot accretion disk. The disk releases more energy than 1 trillion suns. Jets of plasma, accelerated to near light speed by magnetic fields, shoot out from the poles of the black hole, extending for thousands of light years. If you were in a galaxy with an active quasar at its center, the sky would be terrifyingly bright. Radiation levels would be lethal. Anything close to the galactic core would be sterilized. Life wouldn't stand a chance. Fortunately, Sagittarius A star is not a quasar. It's dormant, but that might not always be the case. In about 4 billion years, our Milky Way is going to collide with the Andromeda Galaxy. When that happens, the two supermassive black holes at the centers of each galaxy will eventually merge. The collision will send shockwaves of gas toward both black holes, feeding them enormous amounts of matter in a short time. There's a good chance one or both of them will briefly become quasars. And if that happens, any planets near the galactic center, including potentially Earth if we're unlucky, will be bathed in lethal radiation. The collision won't destroy Earth directly, but the radiation might make it uninhabitable. Of course, we have 4 billion years to figure out a solution. Maybe we'll have moved to another galaxy by then, or maybe we'll have gone extinct long before. Either way, the merger is inevitable, and when it happens, our galaxy will be home to one of the most violent events the universe can produce. Supermassive black holes are proof that size matters. They're not just bigger versions of stellar black holes, they're fundamentally different beasts with the power to control entire galaxies. They're the apex predators of the cosmic food chain, and we're living in one of their hunting grounds. Just when you thought supermassive black holes were as bad as it gets, the universe says, "Hold my beer." There's another category beyond supermassive. We call them ultramassive black holes, and they're so large they make Sagittarius A star look like a pebble. These are black holes weighing 10 billion solar masses or more. At that scale, calling them supermassive doesn't do them justice. They're beyond super. They're ultimate. The largest known black hole in the universe is TON 618. This monster weighs 66 billion times more than the Sun. Let me repeat that. 66 billion suns, crushed into a singularity. Its event horizon has a diameter of about 2,600 astronomical units. 1 AU is the distance from Earth to the Sun. So TON 618's event horizon is 2,600 times that distance. If you put it where our Sun is, the event horizon would extend far past Neptune, past Pluto, deep into the Kuiper Belt. It would swallow the entire solar system and still have room left over. And it's not alone. Astronomers have found dozens of ultramassive black holes lurking in the centers of distant galaxies. Phoenix A, Holmberg 15A, IC 1101. Each one is tens of billions of solar masses. Each one is large enough to hold multiple solar systems inside its event horizon. Here's the really disturbing part. These ultramassive black holes shouldn't exist. At least, not according to what we understand about black hole growth. Even if a black hole fed constantly for the entire age of the universe, it shouldn't be able to reach these sizes. There are physical limits to how fast a black hole can grow. When a black hole feeds, the infalling matter heats up and releases radiation. That radiation pushes back against more matter trying to fall in. It's called the Eddington limit, and it sets a maximum feeding rate. If a black hole tries to eat faster than the Eddington limit, the radiation pressure blows the food away before it can be consumed. Based on this limit, a stellar black hole starting 13 billion years ago at the dawn of the universe should only be able to grow to a few million solar masses by now. Certainly not billions, and definitely not tens of billions. And yet, here they are, ultramassive black holes that broke the rules. So how did they get so big? We have a few theories, none of them comforting. One possibility is that they cheated. Maybe they formed from direct collapse in the early universe, starting at 1 million solar masses instead of 10. That would give them a massive head start. Or maybe they found ways to exceed the Eddington limit, feeding in chaotic bursts that allowed more matter to fall in before radiation could push it away. Another theory is that they grew through mergers. When galaxies collide, their central black holes eventually merge too. If enough galaxies merged in the same region, their black holes would keep combining, growing exponentially with each collision. Over billions of years, this could produce an ultramassive black hole. But even that has problems. Galaxy mergers take time. Black hole mergers take even longer. The math doesn't quite work out for some of the oldest ultramassive black holes we've observed. there might be something fundamental we're missing. Some exotic feeding mechanism, some unknown physics at extreme scales, something that allows these monsters to grow faster than we think possible.
Or maybe, and this is the disturbing part, these black holes are older than the universe itself. No, I'm not suggesting they're supernatural, but what if our timeline is wrong? What if the universe went through cycles before the Big Bang, and some of these black holes are relics from previous iterations? It's wild speculation, but ultramassive black holes make us ask wild questions. Let's talk about what would happen if you fell into one. With a stellar black hole, spaghettification kills you before you reach the event horizon. The tidal forces are too strong. But ultramassive black holes are different. They're so massive, and their event horizon so large that tidal forces near the horizon are actually quite gentle. If you fell into TON 618, you'd cross the event horizon and not feel a thing. No stretching, no pain, nothing. You could theoretically survive for hours inside the event horizon before tidal forces finally became strong enough to kill you near the singularity. But here's the horror. From the moment you cross, you're dead. You just don't know it yet. There's no escape, no rescue. Even if you had a spaceship that could travel faster than light, which is impossible, you still couldn't escape because inside the event horizon, all paths lead inward. Forward in space becomes forward in time, toward the singularity. You'd have time to think about it, time to realize your fate, time to watch the universe outside fade away as you fall deeper into darkness. And then, eventually, you'd reach the singularity and be annihilated. That's the true horror of ultramassive black holes. They're patient. They don't just kill you. They give you time to understand that you're going to die and there's nothing you can do about it. And they're everywhere. Every massive galaxy probably has one. The universe is filled with these cosmic executioners, sitting at the centers of galaxies, waiting. Some are feeding, some are dormant, but all of them are growing slowly, inevitably, over billions of years. One day, in the far future, long after the last stars have burned out, these ultramassive black holes might be the only things left in the universe, drifting through eternal darkness, slowly evaporating through Hawking radiation over timescales so long they make the current age of the universe look like a blink. And when they finally evaporate, the universe will be truly empty, cold, dark, and dead. That's the ultimate fate predicted by thermodynamics, heat death. And ultramassive black holes are the final guardians before that eternal silence. Pleasant dreams. Now we're entering theoretical territory. Everything up until now, stellar, supermassive, ultramassive black holes, we've observed them. We know they're real. But the universe might contain types of black holes we've never directly seen. Monsters, hiding in the shadows of theory and mathematics. First up, primordial black holes. And these might be the most terrifying of all because they could be anywhere, in any size, and we'd have almost no way of detecting them. Here's the idea. In the first fraction of a second after the Big Bang, the universe wasn't smooth. There were tiny fluctuations in density, little regions where matter was slightly more concentrated. If any of those regions were dense enough, they could have collapsed directly into black holes before the universe even had time to form its first atoms.
These wouldn't be stellar black holes from dying stars. They'd be primordial black holes, formed from the raw quantum foam of the newborn universe. And unlike stellar black holes, which have a minimum mass of about 3 suns, primordial black holes could be any mass, any size, from smaller than an atom to larger than a planet. Let's start with the small ones. A black hole of the mass of a car would have an event horizon smaller than an atom. It would evaporate almost instantly through Hawking radiation. But what about something bigger? A black hole with the mass of a mountain. That would have an event horizon about the width of a human hair. And it would be stable.
It would take trillions of years to evaporate, far longer than the current age of the universe. Which means if any formed in the Big Bang, they're still out there. Now, imagine billions of these things scattered throughout the galaxy. Invisible, undetectable, drifting through space at thousands of kilometers per second. If one passed through Earth, it wouldn't swallow the planet. It would be moving too fast. But it would punch a hole straight through, vaporizing everything in its path. You wouldn't see it coming. No warning, no time to react. Just a needle of infinite density moving at cosmic speeds, leaving a trail of destruction. If it went through a city, hundreds of thousands dead in an instant. If it went through your body, you'd be two separate pieces before your brain could process pain. Fortunately, this probably hasn't happened. If mountain mass primordial black holes were common, we'd have seen evidence by now. Unexplained explosions, mysterious deaths, strange geological formations. The fact that we haven't suggests they're either very rare or don't exist at all. But here's where it gets interesting. Some scientists think primordial black holes might solve one of the biggest mysteries in cosmology: dark matter. Dark matter is the invisible substance that makes up 85% of the matter in the universe. We know it exists because we see its gravitational effects. Galaxies rotate too fast to be held together by visible matter alone. There must be something else, something we can't see, providing extra gravity. For decades, physicists assumed dark matter was some exotic particle. WIMPs, axions, neutralinos, particles that barely interact with normal matter. Entire experiments have been built to detect them. So far, nothing. But what if dark matter isn't a particle at all? What if it's primordial black holes? Black holes are invisible, check. They have mass, check. They clump around galaxies, check. They don't emit light or interact electromagnetically, check. On paper, primordial black holes fit every requirement for dark matter. If this is true, then right now, as you're reading this, thousands of primordial black holes are passing through your body every second. Tiny ones, maybe the mass of an asteroid, with event horizons smaller than a proton. You wouldn't feel them. They'd pass through the spaces between your atoms like ghosts. But they'd be there. The missing mass of the universe, invisible and untouchable, woven through everything. There's some evidence for this. In 2015, LIGO detected gravitational waves from two black holes merging. The masses were around 30 suns each, heavier than most stellar black holes should be. Some scientists suggested these might be primordial black holes, not stellar ones. Since then, we've detected dozens more mergers. Some fit the profile for primordial black holes, others don't. The jury is still out. If primordial black holes do exist, they could come in wildly different sizes. We've talked about small ones, mountain mass to planet mass. But what about large ones? A primordial black hole with the mass of 10,000 suns would be indistinguishable from a stellar black hole. We have no way to tell the difference just by looking. It could be hiding in plain sight. Even more disturbing, some primordial black holes might be intermediate mass, filling the gap between stellar and supermassive. We've been looking for intermediate mass black holes for decades, with limited success. What if the reason we can't find many is because they're not stellar remnants? What if they're primordial, scattered randomly through the universe, instead of sitting in predictable locations like galactic centers? And here's the final disturbing thought. If primordial black holes formed in the early universe, and if they're stable enough to survive to the present day, then they're the oldest objects in existence. Older than stars, older than galaxies, older than planets. They're fossils from the Big Bang, carrying information about the universe's first moments. If we could study one up close, we might learn things about the early universe that no other object could teach us. The problem is getting close to one without dying, and first we'd have to find them, which brings us back to the central problem. They're invisible. Unless they're feeding
or unless they pass in front of a bright star and we happen to notice the gravitational lensing, primordial black holes are undetectable. They could be everywhere or nowhere, and we'd barely know the difference. Sleep tight. Up until now, we've talked about black holes defined by two properties, mass and spin. But there's a third property that almost never gets mentioned, electric charge. In theory, a black hole can be electrically charged. We call these Reissner-Nordström black holes if they're not spinning, or Kerr-Newman black holes if they are. And if they exist, they're even weirder than normal black holes. Here's the setup. When a black hole forms from a collapsing star, it inherits three things: the star's mass, the star's angular momentum, which is its spin, and the star's electric charge. Most stars are neutral, equal amounts of positive and negative charge. So most black holes should be neutral too. But what if one isn't? What if a black hole somehow accumulates a net electric charge? This could happen in a few ways. Maybe it swallows more electrons than protons. Maybe it forms in an environment with asymmetric charge distribution. Maybe it's hit by a massive burst of charged particles. Whatever the cause, the result is a charged black hole, and the physics get very strange. A charged black hole has two event horizons, an outer one and an inner one. Between them is a region where the geometry of spacetime is even more distorted than usual. And inside the inner horizon, the math suggests something impossible: a ring singularity instead of a point singularity. The singularity in a normal black hole is a point of infinite density. But in a rotating or charged black hole, it's a ring. And if you could somehow pass through the ring without being destroyed, you might emerge somewhere else. Another universe, another time, another region of space-time entirely. This is where black holes start sounding like science fiction. And to be clear, this is probably science fiction. Most physicists think the inner horizon is unstable. Any attempt to pass through it would trigger a cascade of destructive effects that would kill you long before you reach the ring's singularity. But the math allows it, and that's unsettling. Here's another weird property of charged black holes. They repel objects with the same charge. Normally, black holes attract everything through gravity. But if a charged black hole has a negative charge and you throw negatively charged particles at it, the electromagnetic repulsion can actually overcome gravity. This means, in theory, you could hover near a charged black hole without falling in, held up by electromagnetic forces. Of course, the intense radiation and tidal forces would still kill you, but you wouldn't be pulled toward the event horizon. You'd just be slowly cooked while floating in place. So why don't we see charged black holes everywhere? The answer is that electric charge doesn't stick around. If a black hole has a net negative charge, it will attract positive particles and repel negative ones. This quickly neutralizes it. Within a cosmically short time, maybe a few seconds or minutes, any charge would be balanced out by the surrounding environment. For a charged black hole to stay charged, it would need to be in a region of space with no particles, a perfect vacuum. And space is never a perfect vacuum. There's always something floating around, even if it's just a few hydrogen atoms per cubic meter. That's enough to neutralize a charged black hole over time. So charged black holes, if they exist at all, probably don't stay charged for long. They're transient phenomena, flickers of exotic physics before settling into ordinary, uncharged black holes. But here's a disturbing possibility. What if there's a charged black hole in a region of space that's truly empty? Deep intergalactic voids where the density of matter is unimaginably low. Could a charged black hole survive there indefinitely, maintaining its charge for billions of years? And if so, what would happen if something eventually fell into it? Would the inner horizon remain stable? Would the ring singularity open a door to somewhere else? We don't know. And we probably won't know unless we somehow manage to create a charged black hole in a lab, which is so far beyond our current technology, it might as well be magic. Or unless we detect one in nature, which seems equally unlikely. For now, charged black holes remain theoretical curiosities, footnotes in textbooks, mathematical possibilities that probably don't matter in the real universe. But they remind us that black holes are more complex than they first appear. Mass, spin, and charge. 3 numbers that completely define a black hole's external properties. Everything else, the history of what fell in, the details of the matter that formed it, all of that information is erased. Or is it? That question leads us to one of the deepest paradoxes in physics, but we'll save that for later. For now, just know this. If charged black holes do exist, they're yet another flavor of cosmic nightmare hiding in the equations. Black holes can spin, and when they do, they drag space-time itself around with them. This is called frame dragging, and it's one of the most mind-bending predictions of general relativity. But there's a limit to how fast a black hole can spin. Push beyond that limit, and something breaks. What breaks? Reality itself. Let's start with normal spinning black holes, called Kerr black holes, after physicist Roy Kerr, who first solved the equations. When a massive star collapses, it's usually rotating. That rotation doesn't go away. It gets concentrated into the black hole, spinning it up like a figure skater pulling their arms in. As a black hole spins, it drags space-time around with it. Near the event horizon, this effect is so strong that nothing can stay still. You'd be forced to orbit the black hole whether you wanted to or not, dragged along by the rotating space-time itself. This region is called the ergosphere, and it's one of the strangest places in the universe.
Some scientists think advanced civilizations might do this, build megastructures around spinning black holes to harvest their rotational energy. It's the ultimate power source, millions of times more efficient than nuclear fusion. But good luck building the infrastructure to pull it off. Now, here's where things get disturbing. A black hole's maximum spin is determined by its mass and angular momentum. There's a specific ratio where the black hole is spinning as fast as it possibly can without breaking. This is called an extremal black hole. At extremal spin, weird things happen. The event horizon and the inner horizon, the ones we talked about with charged black holes, merge into a single surface. The ergosphere extends all the way down to the horizon, and the ring singularity becomes razor thin, almost one-dimensional. Most disturbing of all, the event horizon of an extremal black hole can theoretically become a naked singularity. In other words, if you could spin a black hole just a tiny bit faster than the maximum allowed, the event horizon would disappear entirely. The singularity would be exposed to the outside universe. This is called a naked singularity, and it's a cosmic horror. Singularities are places where the laws of physics break down. Infinite density, infinite curvature, infinite everything. The event horizon acts like a curtain, hiding this breakdown from the rest of the universe. But a naked singularity would have no curtain. The universe's rulebook would be ripped up and exposed for everyone to see. Most physicists find this idea so disturbing that they've proposed the cosmic censorship hypothesis. The universe doesn't allow naked singularities to exist. Whenever conditions would create one, something intervenes to prevent it. Maybe the black hole sheds angular momentum before reaching extremal spin. Maybe quantum effects stabilize the event horizon. Maybe the universe just says no, and we don't know why yet. So far, we've never observed a naked singularity, and most theoretical models suggest they can't form. But the math allows them, and that's unsettling. If a naked singularity did exist, what would it look like? What would happen if you got close to one? Honestly, we don't know. The equations break down. Physics stops making predictions. Anything could happen. Time travel paradoxes, violations of causality, spontaneous creation of matter and energy. It's impossible to say because the very framework we use to describe reality fails at a naked singularity. Some scientists speculate that approaching a naked singularity might create closed time-like curves, paths through space-time that loop back on themselves. In other words, time travel. You could potentially fly toward a naked singularity, loop around it, and emerge in your own past. Of course, you'd also probably be ripped apart by tidal forces or fried by radiation or destroyed by quantum effects we don't understand, but ignoring those details, time travel might be possible. This connects to a broader question. Can black holes be used for time travel? The answer is complicated. General relativity allows for time dilation. If you orbit close to a black hole and then fly away, less time will have passed for you than for people far from the black hole. When you return, you've traveled to their future.
But traveling to the past, that's much harder. You'd need a rotating black hole, extremely fast spin, and the ability to navigate through the inner horizon without dying.
Most physicists think it's impossible, but a few think it might work under very specific, very unlikely conditions. Extremal black holes sit at the boundary between what's allowed and what breaks the universe. They're spinning so fast that one more nudge would tear reality apart. And somewhere out there, there might be black holes spinning very close to this limit. Some of the supermassive black holes we've observed are spinning at more than 90% of the maximum. They're not quite extremal, but they're close. And every time they swallow matter, their spin changes slightly. Could one of them eventually hit the extremal limit? Could the universe's cosmic censorship fail just once and give us a naked singularity? We don't know. And part of me hopes we never find out. Because if we do, it means the universe is stranger and more dangerous than we ever imagined. All right, here's where we step fully into the realm of the bizarre. For every solution to Einstein's equations that predicts black holes, there's a mirror solution that predicts something else: white holes. A black hole is a region of space-time where nothing can escape. A white hole is the opposite, a region where nothing can enter, but everything exits. Think of it like a movie of a black hole played in reverse. Matter and energy explode outward from a singularity, bursting into the universe. The event horizon still exists, but it's reversed. Instead of being a one-way door in, it's a one-way door out. Anything inside the white hole is ejected. Anything outside can never get in, no matter how hard you try. Sounds crazy, right? It is. And almost no physicists believe white holes actually exist, but the math allows them, and that's good enough for me to talk about them. If a white hole did exist, what would it look like? From the outside, it would be bright, blazingly bright. Matter constantly erupting from the event horizon, exploding outward in all directions. It would be the opposite of a black hole's accretion disk. Instead of matter spiraling in and heating up, matter would spiral out and cool down. You couldn't touch it. If you tried to fly toward a white hole, you'd be pushed away. Not by any force, but by the structure of space-time itself. Inside the event horizon, every direction you can move points outward, away from the singularity. You can't move toward it any more than you can move backward in time. Wait, did I just say backward in time? Yeah, white holes are intimately connected to time. In fact, some interpretations suggest that a white hole is what the Big Bang looks like from the inside. Think about it.
The Big Bang was a moment when all the matter and energy in the universe exploded outward from a single point. Nothing could exist before it. Nothing could enter it from outside. It's a one-way event in time, just like a white hole is a one-way event in space. Could the Big Bang actually have been a white hole? A massive explosion of matter from a singularity, ejecting everything that would become our universe? Some cosmologists have played with this idea. It's speculative, and most don't take it seriously, but it's not completely absurd. Here's another weird possibility. Black holes and white holes might be connected. Some solutions to Einstein's equations allow for a black hole and a white hole to be two ends of the same object, connected by a tunnel through space-time. This tunnel is called an Einstein-Rosen bridge, but you probably know it by its science fiction name, a wormhole. In theory, you could fall into a black hole, travel through the wormhole, and emerge from a white hole somewhere else in the universe, or somewhen else, or in another universe entirely. Of course, this doesn't work in practice. Even if such a wormhole existed, it would be unstable. The slightest disturbance, even a single photon of light, would cause it to collapse. You'd be crushed before you made it through. And that's assuming you survived the tidal forces near the black hole singularity in the first place, which you wouldn't. But let's ignore practicality for a moment and imagine what traveling through a black hole-white hole wormhole would be like. You cross the event horizon of the black hole, falling inward. Time dilation makes the outside universe age rapidly from your perspective. You watch galaxies live and die in seconds. Then you pass through the throat of the wormhole, a narrow tunnel where space and time twist into impossible shapes. And then you emerge from the white hole, exploding outward along with everything else trying to exit. If you somehow survived, you'd find yourself in a completely different region of space, possibly a different time, possibly a different universe with different laws of physics. It's pure fantasy, but it's fantasy grounded in real mathematics. The equations allow it, even if reality doesn't cooperate. So why don't we see white holes? If they're allowed by the equations, why haven't we detected any? The simplest answer is that they're unstable. Even if one formed somehow, maybe in the early universe, it wouldn't last long. Matter from the surrounding environment would eventually fall onto it from the outside. But wait, I just said nothing can fall into a white hole. That's true at the event horizon. But matter could still orbit nearby, and the white hole's gravity would pull things toward it. Eventually, enough matter would accumulate that it would flip the white hole into a black hole. The reversal wouldn't last. Another possibility is that white holes do exist, but they're invisible to us because they're in the past. Remember, a white hole is a time-reversed black hole. If black holes are the future endpoints of collapsing stars, white holes would be the past starting points. They'd exist for a brief moment and then instantly convert into black holes. By the time we look at the universe, all the white holes are already gone, replaced by the black holes we observe today. Some scientists have suggested that certain high-energy cosmic phenomena might be white holes. Gamma-ray bursts, for example. These are the brightest explosions in the universe, releasing more energy in a few seconds than the sun will emit in its entire lifetime. Could they be white holes erupting for a brief instant before collapsing?
Probably not. We have better explanations for gamma-ray bursts, things like colliding neutron stars or hypernovae. But the fact that we're even considering white holes shows how little we understand about the most extreme events in the cosmos. One more disturbing thought. If a black hole and a white hole can be connected by a wormhole, and if a white hole might be what the Big Bang looked like, does that mean our universe emerged from a black hole in another universe? Could every black hole in our universe be spawning new universes on the other side? This idea is called the black hole cosmology hypothesis, and it's deeply speculative. But it raises a terrifying question.
If we're inside a black hole from a parent universe, does that mean we're doomed to collapse into the singularity eventually? Is the expansion and eventual heat death of our universe just a very slow fall toward an inevitable end? No one knows. And frankly, even if it were true, there's nothing we could do about it. If our entire universe is inside a black hole, the event horizon is billions of light years away, receding faster than we could ever travel. We're stuck here, whether we like it or not. White holes are the ghosts of black hole physics. Allowed by the math, probably impossible in reality, but too fascinating to ignore. They're a reminder that the universe might contain things we've never seen, and maybe never will. And sometimes, that's more disturbing than any monster we can observe. Everything we've talked about so far assumes that singularities are real, that at the center of every black hole is a point of infinite density where physics breaks down. But what if that's wrong? What if singularities don't actually exist? This is where quantum mechanics crashes into general relativity, and the result is some of the weirdest ideas in modern physics. One of them is called a Planck star. Here's the problem. General relativity says that when you compress matter enough, it collapses into a singularity. Infinite density, infinite curvature, infinite everything. But quantum mechanics says that's impossible. At the smallest scales, around 10 to the minus 35 meters, quantum effects take over. Space and time themselves become grainy and discrete. You can't compress something smaller than the Planck length because there's no such thing as space smaller than that. So, what happens when these two theories collide? One possibility is that the singularity is replaced by something else, a Planck star. A Planck star would be an incredibly dense, but not infinitely dense, core at the center of a black hole. It would be held up not by any normal force, but by quantum pressure, a repulsive effect that emerges at extreme densities when quantum mechanics becomes important. From the outside, you wouldn't be able to tell the difference between a black hole with a singularity and a black hole with a Planck star. The event horizon looks the same either way. But inside, the physics would be radically different. If you fell into a black hole with a Planck star, you'd still be doomed. You'd still cross the event horizon, still be stretched by tidal forces, still be unable to escape. But when you reach the center, instead of hitting a singularity and being annihilated, you'd hit a Planck star, and, well, we're not sure. Maybe you'd be absorbed into it, your mass adding to its quantum structure. Maybe you'd bounce off it. Maybe you'd quantum tunnel through it and emerge somewhere else. All of this is speculation. We don't have a theory of quantum gravity, so we don't really know what happens at these scales. But the idea of a Planck star solves one of the biggest problems in physics. It eliminates the singularity, replacing an infinity with something finite and calculable. There's another related idea called loop quantum gravity, or LQG. This is a theory that tries to unify quantum mechanics and general relativity by making space-time itself quantum. In LQG, space isn't smooth. It's made of tiny loops, like a fabric woven from threads at the Planck scale. When applied to black holes, LQG predicts something similar to Planck stars, but even weirder. As matter collapses toward the center, quantum effects cause it to bounce. The collapse reverses, and the black hole starts expanding from the inside. Eventually, it explodes in what's called a black hole to white hole transition. Think of it like a ball bouncing. The collapse is the ball falling, the singularity is the moment it hits the ground, but instead of stopping, quantum effects make it bounce back up, reversing the collapse and turning the black hole into a white hole that ejects everything that fell in. The catch is that this happens inside the event horizon, where time is so dilated that from the outside, it looks like it takes trillions of years. So even though the black hole is technically rebounding, we'd never see it happen in the lifetime of the universe.
This solves the black hole information paradox, which we'll get to in a moment, but it also raises a disturbing question. If black holes eventually explode, and if they take longer than the current age of the universe to do so, could there be primordial black holes from the early universe that are just now starting to explode? Could we detect these explosions as mysterious bursts of energy from deep space? So far, no one's seen anything that fits the profile, but we're looking. All of these ideas, Planck stars, loop quantum gravity, quantum bounces, are attempts to fix the problem of singularities, and they all point to the same conclusion. Black holes are not the end of physics. They're laboratories where quantum mechanics and gravity collide, and whatever happens in there might be the key to understanding the deepest laws of nature. If we ever develop a full theory of quantum gravity, it will probably tell us what's really at the center of a black hole. And when it does, we might discover that singularities were never real, that the universe is strange, but not infinitely strange, that there's always one more layer of physics to uncover.
Or maybe we'll discover something worse, that singularities do exist, that infinities are real, and that the universe truly does break down in certain places, that some questions don't have answers because the universe itself doesn't have rules there. Either way, the truth is waiting, hidden behind the event horizons of a billion black holes, daring us to figure it out. Now we come to one of the most disturbing implications of black holes. Not something about how they kill you, but something about what they do to information itself. This is called the black hole information paradox, and it threatens to unravel everything we think we know about how reality works. Here's the setup. In quantum mechanics, information is never destroyed. If you know the complete quantum state of a system at one moment, you can, in principle, calculate its state at any other moment, forward or backward in time. The universe, according to quantum mechanics, is deterministic and reversible. Information is conserved. But black holes seem to violate this. When something falls into a black hole, all the information about it disappears behind the event horizon. The black hole's external properties, mass, spin, and charge, tell you nothing about what fell in. A black hole formed from collapsing hydrogen looks identical to one formed from collapsing oxygen or iron or people. All the details are erased. Okay, so the information is hidden inside the black hole. No problem, right? It's still there, just inaccessible. But then Hawking radiation enters the picture. Hawking showed that black holes slowly evaporate, emitting thermal radiation and losing mass over time. Eventually, the black hole evaporates completely and disappears. And here's the problem. Hawking radiation is thermal, meaning it's random. It doesn't carry information about what fell into the black hole. It's just heat. So if a black hole evaporates completely and all it leaves behind is random thermal radiation, where did the information go? It can't have been destroyed because quantum mechanics says that's impossible. But it can't be in the Hawking radiation because that's random. And it can't still be in the black hole because the black hole no longer exists. This is the paradox. Either quantum mechanics is wrong and information can be destroyed, or general relativity is wrong and something weird happens with Hawking radiation, or our understanding of both theories is incomplete. Physicists have been arguing about this for 50 years. Stephen Hawking originally believed information was destroyed, that black holes were exceptions to the rules of quantum mechanics. But later in his life, he changed his mind and proposed that information might be encoded on the event horizon in a holographic way. When the black hole evaporates, the information is released in the Hawking radiation, but in such a scrambled form that it's effectively irretrievable.
Other physicists propose different solutions. Maybe information is stored in Planck stars. Maybe it leaks out through quantum effects we don't understand yet. Maybe black holes never fully evaporate and leave behind remnants. Maybe information doesn't just exist in our three-dimensional space, but is spread across higher dimensions we can't perceive. One of the most radical ideas is that the event horizon itself is an illusion, that what we think is a smooth, empty boundary is actually a seething wall of fire called a firewall. In this picture, anything crossing the event horizon would be instantly incinerated by quantum effects, and the information would be preserved in the radiation emitted. But this violates other principles of general relativity, creating new paradoxes to replace the old ones. No one has solved the information paradox yet, and until we do, it hangs over physics like a dark cloud. Because if black holes really do destroy information, it means the universe is not deterministic, that the past doesn't uniquely determine the future, that randomness and chaos can erase history itself. And here's the existential nightmare. You are information. Your thoughts, your memories, your personality, all of it is encoded in the quantum states of the atoms in your brain. If you fell into a black hole and that information was destroyed, would you be truly gone? Not just dead, but erased from reality itself, as if you never existed? Some interpretations of the paradox say yes, that crossing an event horizon doesn't just kill you, it unmakes you on the most fundamental level. You wouldn't just die, you'd be deleted from the universe's records. Other interpretations say no, that the information is preserved somehow, somewhere, even if we can't access it, that you'd live on as a pattern encoded in Hawking radiation, scattered across the cosmos, unreadable but still technically existent. Neither option is comforting. Black holes force us to confront questions that most people never think about. What is information? What does it mean for something to exist? Is the universe a computer, processing data according to rules, or is it something stranger? Can reality truly have holes in it? Places where the rules don't apply? These aren't just philosophical questions. They're scientific ones, and they're unsolved. Black holes sit at the intersection of our two best theories, quantum mechanics and general relativity, and they reveal that we're missing something, some deep principle, some hidden law that would make everything make sense. When we find it, and we will eventually, it will change everything. It might tell us that black holes aren't destroyers of information, but transformers, that the universe is more interconnected than we realize, that what goes into a black hole doesn't disappear, but becomes part of something larger and stranger. Or it might tell us that the universe is crueler than we thought, that some things, once lost, are lost forever, that oblivion is real. Either way, black holes are more than just cosmic objects. They're mirrors reflecting our deepest questions back at us. And until we understand them fully, we won't understand the universe or ourselves. We've journeyed through every type of black hole humanity has discovered or imagined, from stellar remnants born in supernovae to ultramassive monsters that anchor galaxies, from theoretical primordial seeds scattered in the darkness to impossible white holes that spit matter out instead of swallowing it. We've seen how black holes stretch you into spaghetti, freeze you in time, and scramble your information beyond recognition. We've explored the boundaries where physics breaks down and reality itself becomes negotiable. And through it all, one thing becomes clear. Black holes are the universe's way of telling us we don't understand anything. Every time we think we've figured them out, they reveal new mysteries, new paradoxes, new reasons to question everything we thought we knew. They're not just objects in space. They're tests, challenges, puzzles wrapped in event horizons daring us to solve them. And the most terrifying part? We're just getting started.
Every new telescope, every new gravitational wave detector, every new theory brings us closer to understanding these cosmic nightmares. But it also reveals how much more there is to learn. Somewhere out there, right now, black holes are forming, stars are collapsing, galaxies are merging. And with each event, the universe creates a new hole in space-time, a new trap door to nowhere. Or maybe to somewhere we haven't imagined yet. So here's my question for you. Which type of black hole scares you the most? The stellar ones that could be drifting near Earth right now? The ultramassive ones that could swallow our solar system without noticing? The primordial ones that might be passing through your body as you read this? Or the theoretical ones, the charged black holes, extremal black holes, Planck stars, and white holes that remind us how little we truly know? Drop your answer in the comments. And if you want to explore more cosmic nightmares, hit that subscribe button. Because the universe is full of terrors, and we're just getting started. Thanks for watching. And remember, every time you look up at the night sky, you're staring into a darkness that stares back. The abyss is real, and it's waiting.